the speakers will be introduced, I just want to give a brief update. Earlier this morning I met at 9 a.m. with the Dean of the Graduate School here at Harvard, trying to advocate that we will have a group of graduate students, potentially also undergrads, that are focusing on black holes for their physics, PhD. And if we get this approved, I mean, the meeting took about 45 minutes. The rationale, I should say, is that we have an interdisciplinary center that involves people from different departments, at least 4 departments: astronomy, physics, math, and philosophy and history of science. It would make sense for graduate students interested in black holes to actually take courses in different departments and not just be focused on their own discipline. I mean, we look at some of the more senior colleagues and they are very focused, and if you just let them dictate what the students will do, they will be very focused as they are. And we think it's actually very important to have a broader perspective, and that's why we have this center. So the idea is to have a program where students can take classes in different departments as part of their education to become graduate students of the Black Hole Initiative Consortium. And so it seemed like they were receptive to the idea. We shall see if they approve it. So the hope is, I hope to hear in the near future, and I'll let everyone know. And that will obviously link the center to the university, give it a flavor of an educational center, not just a research center. So that's the hope. We'll start with Brian.
Yeah, let us start. Our first speaker today is Burkhard Schwab. He is a physics postdoc here at Harvard, and he will tell us about black hole absorption rates from conservation loss.
Thank you. Thanks for the nice introduction. And also thanks for the invitation to talk here. Yeah, so today I'm going to talk a little bit about a project that I did together with Stephen Avery. And it really is all in the title. Well, it's actually not true. So I need to put some boundaries to this statement. So first of all, I'm going to talk about absorption rates for electromagnetic radiation. Then I'm going to talk about very low energy electromagnetic radiation. And yeah, that's it. And since I'm talking about boundaries, this is going to be a black hole in asymptotically flat space-time. And so before I'm going to tell you more about this, I'm just going to set some of the boundaries. So asymptotically flat space-time is shown here in this Penrose diagram. And there are some interesting points that are marked out. So first of all, there is future and past time-like infinity. These are the points where massive particles begin and end their lives. Then there's I0, which is spatial infinity, where nothing much really is happening. So in particular, things cannot reach out here, but I'm going to talk about this later on. And third of all, there is null infinity, and this is where radiation begins and ends its life. So radiation comes from here and goes out to square plus. So additionally, I have a little cartoon here of spatial infinity, and I blew up this point a little bit. But first of all, this is really a cartoon. You shouldn't take this as a proper depiction. But it's important. What I wanted to make clear is that there's actually a dimension to I0 that is suppressed in this diagram here, and so really this, because think of I0 as the boundary of a spatial slice. So this is one at a specific time. So if I take a spatial slice in my asymptotic flat space-time and I go to very far distances from the origin, then essentially the boundary of this looks like a sphere, and then I have for every parameter value of t of the time, I get an additional direction. So this at I0 we really have r times s2. Okay. So
about Penrose diagram.
That's not true about the yeah, that's correct. That's correct. But it's going to be important for me later on that there is such a topology of R times S2. Indeed, in the Penrose diagram, this is really a point.
But that's what Ashtekar did, right? When it's a point, you want to resolve it, and he blew it up to R cross S2.
That's correct. Yes.
Yeah,
So if you go to hyperbolic coordinates,
you just don't want to get confused that photons can bounce off and come back in finite affine parameter, which that
that's right. That's why I also said that null infinity nothing really can reach out there. So okay.
You're not actually blowing up anything, are you? You're just describing a slice.
I'm just describing.
Okay, so it's not a blower.
Well, in this diagram, in the Penrose diagram, this is actually a point.
Well, yeah, okay.
So if you want to discuss this out here, you will have to pull up. Okay, so the black hole I'm going to be discussing is going to be a black hole that lives in asymptotically flat space-time. And as I said, I'm going to talk about how to calculate the absorption rate for electromagnetic radiation. So what I'm going to do is I'll take a classical black hole background, and that can really be any spherically symmetric black hole, and I scatter very low energy light off of it. So essentially I'm just going to calculate the absorption rate by looking what I send in, how much gets absorbed, how much comes out at the other end of the space-time. Okay? These calculations have actually been done in the 70s already, and that has been done by asymptotic matching of the solutions. And today I'm going to show you that this calculation can actually is fully constrained by the use of two conservation laws. Namely, first of all, the conservation of energy, and the second thing I called conservation of canonical momentum. I will have to qualify this a little bit. But this is also known as the soft symmetry in the literature. Okay, so this current here, for our purposes, is going to be this here, and this lambda here is a parameter that depends on space-time. So this is not a fixed global parameter, and the function lambda will be subject to some conditions that I will be talking about later on. When I say conservation of canonical momentum, I really mean that if I try to calculate the charge of this current J, then this is going to be on a spatial slice, and that is going to be F0I, which is the electromagnetic field, which is the canonically conjugate momentum to the photon field. And of course, it's not the full canonical momentum that is conserved here, it's just a particular set of modes that we conserve. Okay, so
You have also Maxwell's equations. Another set of equations for F.
yeah, there's Maxwell's equations and Bianchi identities satisfies all of it. Yeah. And this is conserved, as you can see, this is conserved actually because of Maxwell's equations and the antisymmetry. I mean, I wrote the nabla here, but this is a scalar. Okay, so before I'm going to talk about how to calculate the absorption rate using these two things, I'm going to tell you how to actually get to this current. And for that, I'm going to go back to undergrad physics and tell you about Noether's theorem. Okay, so you've all heard about Noether's first theorem. That's what we learned when we start doing learning about mechanics and about symmetries. And here on this slide, I'm just giving a short derivation of Noether's first theorem. So if I have an action, which is just like this, here's Lagrangian, here's some fields, derivative of fields, and potentially higher derivative of fields, but I'm not going to use this today. Okay. So if I vary this action for any old variation, then I know I can always write the variation like so. This is the equations of motion here, and there's a total derivative here. And we demand the equations of motion to be 0, and this is just a total derivative. Okay. If in particular we have a symmetry variation, then we know that the action should be invariant under this. That means the Lagrangian can maximally change by a total derivative, okay, like this thing here. And using these two equations, then we can immediately derive Noether's equation, which is just that this current is conserved up to the equations of motion. Okay, up to the equation of motion is an important statement here because we will soon see something that is strongly conserved. So this is what in the literature you will often find as weakly conserved. So notice the subtle change between this slide and this slide. Now I'm doing something else. So really what I just presented was warm-up for Noether. That was the easy part. The harder part is when you have local variations. Notice that I don't say gauge variations, I say local variations, by which I mean that the parameter of the symmetry just depends on the space-time point. Okay? And the whole idea of this derivation here was to define energy, the notion of energy properly in GR. Okay? Where of course the variation looks exactly like this because it's because we have diffeomorphisms as the variation parameter. So to go through the derivation, remember from this slide, this is definitely true also for local variations. This is true for local variations if there are symmetries. And if there are symmetries, then Noether's second theorem tells us that for this term here, an additional equation holds, namely that some operator here acting on the equations of motion, on all of the equations of motion, is 0. Okay, this is actually Noether's second theorem. And what is this operator? Well, this operator is really just what you get when you do partial integration and you move all of these derivatives. There's potentially many more derivatives acting on the parameter here over onto the equations of motion in this term. And of course, then you get also an additional total derivative here. But then from the logic from before, we can just take this and that, plug it in here, and that means that J minus S is conserved, strongly conserved, meaning that even before I use the equations of motion, it's conserved. Okay, so that also means, and because this is strongly conserved, that means that, assuming nice behavior, that this can be written as a derivative of a 2 form. Okay, so this was cute and everything, but what will we do with this? As I said before, this type of 2 form is well known in gravity because that type of 2 form is what we're using to calculate, for example, the ADM mass at infinity. So that means I can take this 2 form and integrate it over the boundary of the spatial slice, and what I get is some conserved value. Okay. So the interesting thing is that doesn't just happen in GR. You can also do this for you can also do this in QED or in other gauge theories. So this is from an old slide. I recycled here. Yes, it also works for Young-Mills, but I really want to talk about the QED Lagrangian here for a second. So I can do the variation. The variation, so delta A here would be d lambda. And I go through all of this here, and I end up with this 2 form. Okay. I can also define the current J on the other side, and that would be this here. Okay. And then I can integrate this over a spatial slice, or I can integrate this over K. So you will probably recognize that if lambda is a constant, then this is just f mu nu, and when I integrate this over the boundary of space-time, it gives me just the charge, the total charge on that slice. Okay. If lambda is not 0, and in particular if lambda doesn't become 0 at infinity, then these things have interpretations, and this interpretation was given, and also the word identities for these transformations were given by members in the audience here. And the word identity for the symmetry, however, I have to add that if you really want to do this, you should put this current on a null slice rather than a spatial slice. In the following, I'm going to talk about spatial slices. Then you can derive the word identity for this transformation, and you can do similar things. Of course, A will look differently for gravity, and there, instead of having transformations that become non-zero at the boundary here, you have the BMS symmetries that we heard in this seminar here before. You can do this in supergravity with large supersymmetry transformations that also don't become zero at the boundaries of space-time, and you can do it in SQED. Okay. So now that I've set up this current here, I'm going to tell you how I'm going to calculate the absorption rate for the black hole space-time using it. So first of all, the setup. The setup is I'm going to take some eternal black hole. It's just going to be a background. I'm going to do a classical scattering experiment. So I send some waves into my black hole space-time, and there's no back reaction, and I'm just going to look what I throw in and what comes out, essentially. So again, I gave you here the Penrose diagram, and I gave you here some blown up picture, because this is going to be the picture that I use for the calculation. I put essentially cutoff membranes here and there, and these are these two cylinders that I have here. So the black thing is exactly the point where we have the horizon. Then I have a membrane very close to the horizon, which is the cutoff close to the horizon. Cutoff is distance is delta. And then I have a very large value of r, which is very far away but not quite infinity. And I have two spatial slices here. Okay. So this picture is going to pop up again. Not on this slice, but on the next. Okay. So as a warm-up, I want to do the calculation for the scalar field. The black hole space-time I'm using is going to be this. This is, as you can see, a spherically symmetric black hole space-time. And I put this here in isotropic coordinates. So notice that G is also sitting in front of this rather than just in front of dr. And this means that these functions here, f and g, have the following properties. Close to the horizon, f goes to 0. G is not 0 at the horizon, but smooth. And far away, they become 1, so we recover flat space-time. Okay, so we use this background for the scalar. The scalar has some energy momentum tensor like so. And also, this is a bit obscured by the notation I used here, but the scalar also has a shift symmetry. And this shift symmetry is really a global symmetry and gives you a current like this. Okay, so these are the two pieces of information that I will use to calculate the absorption rate for the S wave of the scalar. Okay?
Sorry, the epsilon is constant, or
It's constant, yeah.
why isn't that shift symmetry why isn't the current the Klein-Gordon current?
Because
Another construction.
I shift. Well, the Klein-Gordon current would give you phi d phi, right? So
Yeah.
this is.
Klein-Gordon current, right? It is 0 for real field configuration.
Oh, that's right.
Right? This
Yeah.
is the shift symmetry.
This is the shift symmetry of the scalar.
So that vanishes in flux. Oh, G mu is not the Einstein tensor. It's the.
No, it's not. Sorry, I wanted to make sure clear that this is not this G. That's
Okay, never mind. Sorry.
That's the metric, yeah. Okay, so now consider these two contour integrals, right? These two contour integrals are just exactly going over the slice, along the black hole, what is it time like, over the slice and back, okay? So what this tells you here that the amount of current that I send in is the amount of current that goes into the black hole, the amount of current that comes out. That's all this equation says, and this is true, of course, for both. additionally, I use this the simplifying circumstance that we are living on an eternal black hole with spherical symmetry, so I can decompose the scalar into modes like these. And as I said, I use low energy, very low energy. So that means that this this product here is going to be much less than 1, even if R is very, very large. Okay? So again, this is energy, this is canonical. This
So why do you need that restriction?
this one?
Omega, yeah.
Yeah, because I can actually only do this calculation for this limit. Okay, you will see it on the next slide. Because in this limit,
There is no back reaction, right?
there's no back reaction.
Yeah, okay.
Well, this makes it even easier, right? Because
Right.
if it's really low energy, then
Then
the
you
approximation is
you
much
guaranteed
better.
that it's not, yeah.
Yeah.
Okay, but you're saying there's something more than that.
Yes, because if I do these two calculations, so I stick now everything in, I know about phi and everything, and I do this calculation, then I find an equation that relates the very far region to the region very close to the black hole, up to terms of order omega squared. Okay, in both cases. So this is the conservation of energy, and this is the conservation of energy, and this is the conservation of the soft current. Then I can take the ratio of these and stick it into the absorption rate, which I can write down, and then I can. And the really important thing is I can go and then remove the regulators. So big R is going to vanish, and when I write RH, I really mean RH plus delta here in all of these equations. But once I stick that into the absorption rate, I can remove R and delta, and I get this result here. And this result is kind of interesting. So first of all, I've been doing this for all dimensions. So D equals P plus 2, and P is the size of the dimension of the sphere. So particularly in 2 dimensions, you can see that the absorption rate for the scalar is actually proportional to the area of the black hole. And the lower the energy becomes, the harder it is for the black hole to actually absorb anything.
So, Bert, can I ask? So the way I'm used to doing this calculation, you just solve the equations in motion near the horizon at infinity, and then you observe that at small frequencies, there's an approximation with overlapping validity. So is what you're saying just that actually in that limit, I didn't really need to know the entire equations of motion? I could have just solved the conservation law, and that
That's
would be
correct.
enough?
Yeah, that's correct.
But you've only using
Even more importantly, for the electromagnetic case, that is also going to be true.
Yeah.
And there, I really have big problems giving the solution to the equations of motion in the middle.
Yeah.
So
But I mean, in this limit, you can just solve the equations in the middle.
You can.
Or some Bessel
That's-
functions or
that's
something,
right. That's right.
Yeah.
you're only using 2 global symmetries, right? And
Yeah.
you're not using the soft symmetries.
I'm not using the soft symmetry here, and as you can see, this is really just the L equals 0 mode. This is really just the S.
Okay,
I'm going to talk about the soft symmetry in a second, and
Alright.
there I'm going to get the result for all L.
I see.
By the way, if you were to just imagine without any gravity,
Mhm.
a sphere, absorbing boundary of a sphere,
Yeah.
scattering waves with low omega on it, will you
Mhm.
get the same answer? Without gravity.
Without gravity,
Just an absorbing sphere. Well, it's interesting to check. My guess is it will be the same.
it might be the same actually in this declaration. Yeah.
So sorry, can I ask, so the issue here, the reason why I only got L equals 0 here is because if you want to gauge the shift symmetry, it only makes sense to gauge the 0 mode, is that right? Because I guess you're gonna gauge the whole thing, if reading out, but, or could you have gotten the L not equal to 0 mode for the scalar?
I don't think you can get the L.
Yes, then I would guess it's related to the fact that you can only gauge the 0 mode of the shift symmetry.
Yeah, that's very true. But I haven't thought about this, and it might be worth thinking about this. As I said, this is a warm-up because I can really get it or you can get all L on the next slide. So, for electromagnetic waves, I derived before this current here, the soft current, and this lambda is a priori a unconstrained function. Okay, it's a scalar function. It's unconstrained apart from gauge compatibility, because, as I said before, this looks exactly like the gauge variation. So if this lambda doesn't satisfy this, then if I do a gauge fixing, this lambda cannot be in there anymore. Okay. So that means lambdas are time independent. Okay. So additionally, I'm going to use again all the symmetries of my space-time. So first of all, I have time translation invariance. And I use that I have spherical symmetry, so I can have these YLMs here. And I use actually that parity is telling me which is telling the two types of polarizations of or two types of photons that I can have apart. And so here I have the so-called gradient mode, and the other spherical vector spherical harmonic is going to give me the so-called solenoidal mode. And I'm not going to talk about this one, because if I try to do that calculation with that one here, I actually get 0. So that doesn't do anything, but there is actually a different symmetry that can tell me about the solenoidal mode. Okay, so what do? I take the temporal gauge, so that means AR equals 0. I solve the Gauss constraint, that means B gets related to C. And then the rest of the equations of motion is just going to give me an equation of motion for C, and these guys here are pretty horrible functions of the parameters of the metric, so F and G. So if I wanted to solve this equation here on the full spatial slice, I'm out of luck essentially. Additionally, I'm going to let B lambda also be decomposed like this, and as I said before, it has no time components, so there's no time here.
Are you putting boundary conditions at large R for lambda LM?
In a second. If you take nothing away from this from this slide here, then only one thing, please. Nothing except for one thing. There are some certain asymptotic limits, namely R goes to large values, and the near horizon limit where this equation here is easy to solve. Okay, this is the flat space solution. Okay, and this is the near horizon solution, and we will pick the infalling solution. Right, we want just infalling waves. Goes to horizon, which is actually the one with the positive sign. And in these limits, the equations of motions are simple to solve. Okay. Now, as I did for the scalar, I'm going to calculate the conservation of energy, okay, and I'm going to calculate the conservation of the soft current, which is the only one that I wrote down here, and I do this on this contour. And when I try doing this, I run into a problem, okay? Namely, I run into the problem that I need to know the solution of the equations of motion on the spatial slices. And this is where lambda comes in, this function lambda, because a priori lambda was unconstrained. If I constrain lambda to satisfy the equations of motion for CR, you remember from here, but at omega equals 0, part equals 0, not just limit or close to, omega equals 0, then it turns out that this is just the hypergeometric differential equation. I can solve this for all R, and the dependence on the spatial slices drops it out entirely, and I get an equation that once again relates the far field with the field very close to the horizon. Okay. Then I use energy conservation. Take the ratio again. I get this equation here. I can solve this, and I get the absorption rate.
So the hypergeometric equation has two parameter family of solutions, right? So are you taking the one that grows at large R, or?
Actually, I need to no, I take the one that goes with 1 over R to the L.
So then your charges are going to vanish, right?
No, that's
Because
no. Sorry. I take the other one. I take the solution which grows. Yeah.
Which grows.
Yeah. Because these guys fall off, towards infinity.
So you're really using the subleading soft symmetry, I think. The leading soft symmetry would give you something trivial, which would be the ones that go to a constant. It's interesting. Anyway,
We can talk about this
Yeah,
later.
yeah.
Maybe that's that could be interesting. Again, if I do this and I plug in the solutions for lambda at large r and close to the horizon, I can actually remove the regulators delta and large r, and this absorption rate here is going to be independent of those. And as you can see, this looks slightly different from the scalar case. First of all, this is a solution for all L. Sorry. Second of all, it's not just proportional to the area of the black hole, but there's this factor of L here. And third of all, it also depends on kind of the shape, on this function g of r here. And so
So
yes.
you had to assume that omega capital R is much less than 1.
Mhm.
The answer doesn't depend on capital R at all.
No, this is
So
the.
wouldn't that mean that really that restriction was unnecessary?
Well, I could equally well have said that omega is much smaller than one of the radius of the
Yeah,
horizon.
but firstly now it's only RH, whereas capital R is some enormous number, right?
That's an enormous number.
Compared to RH, so these are very different scales.
Right, but we will have to, I obscured this in the calculation here, but omega r does pop up and we do have to use
You have to use that,
omega r is smaller than 1. Yeah.
because that's a really small frequency.
It's a very small frequency, yes, yes.
It's the light crossing time of the universe.
Right.
What's the meaning of a wave when your box is smaller than the wavelength? So you're saying that r, the extent of your space-time,
Mhm.
is smaller than the wavelength?
Well,
it's not bigger. R isn't bigger than the universe. It's just bigger than the black hole.
yeah, r is the.
Yeah, but there is no electromagnetic wave to be defined if the scale that you're looking at is smaller than the wavelength. There is no oscillation of the wave. It's just
Yeah.
a constant electric field.
That's essentially what this is calculating. I mean, this is exactly what the soft current is making a statement about.
Okay.
This is actually kind of confusing because I would have thought that the only thing you need to be able to solve the equation is that it's small compared to the horizon radius. So that omega times r horizon is small. That makes the difficult part of the calculation tractable by just solving the equation. So why I assume that was what you meant actually when you said omega r is small. I mean, why is the box is irrelevant, right? I mean, out of the box everything is.
Yeah, I think you're actually right. The box
Yeah,
should be
I thought
very.
that's what you
It
meant. Yeah.
should be
I think you just mean
yeah,
on the
sorry.
horizon.
Yeah, no, this is right. Sorry, you're right.
Yeah.
Makes more sense, good.
No, omega r. Yes, omega r h plus omega.
Yeah.
Okay, sorry about that. Okay. Yeah. So, the important thing here is that this was calculated purely from using conservation statements. Okay, so what have we learned? That means I can calculate the low energy absorption rates for electromagnetic waves, for spherical symmetric black holes, just using symmetries. And I only need to know the solution of the omega equals 0 equation of motion on the whole of the space-time. Everything else I just need to know in the limits. A generalization to Kerr spacetimes may be possible, but it's much harder. For the scalar case, it's very similar, but for E and M, it requires a lot of work. The generalization to gravitational waves is possible because there we know we also have a soft current, and that is determined by the BMS symmetries. And in general, we try to make inroads in understanding these conservation laws on spatial slices.
So you say the scalar case for Kerr, you can do it. You will get super radiance?
I haven't tried to do it,
You should
but
get it.
You should, right?
you should get it.
Yeah.
Yes, that's
Okay,
right.
that'll be
Yeah.
something,
Yeah.
if it is that easy to do.
It should be possible to do
just
that.
from the symmetry.
Yeah.
Okay.
I understand, the implications of this. So you have the radiation on the outside moving in the space-time defined by the black hole. The black hole absorbs the radiation, and is it, in your formalism, is it possible to take those effects into account, or
On the black hole?
on the black hole and the way it will then change the space-time
So
in which other radiation
This was the
moves?
caveat I made before. There's no back reaction, so that means that the black hole does not change. Okay, and in this calculation, this is a good approximation because we're talking about very, very low energy.
Now, I understand that it's fine for the calculation, but I'm trying to now relate it to doing a problem where you actually have radiation that may be absorbed by a real black hole. It would be good to understand the regimes in which you can actually apply all of this.
Right. I mean, we haven't tried to do this.
That would be an interesting.
That would be interesting. Yes.
Let's think closer. There is a whole book by Chandrasekhar on scattering things on black holes. He tried to scatter everything, but it's a whole book, and you do it much faster than his.
Yes, I mean, in the book they're using the asymptotic matching procedure.
That's a good book to read to understand that this is progress.
He dedicated a decade of his life to this.
Yes.
Okay, well, Jeff is setting up, our second speaker today is Jeff Oishi. He's a professor of physics at Bates College in Maine. He's also semi-local, not because Maine is close, but because he sometimes lives in Cambridge, so you could ask him about that afterwards. He's an expert in computational physics and fluid dynamics, which he's applied to a wide range of astrophysical problems. He's also part of an exciting new project called the Daedalus Project, which might solve all of your PDE problems. So he might tell us about that today.
Does it fly? No. All right. Well, I could spend a long time trying to get this stuff off of the screen, but I'm gonna not. So, thanks a lot for inviting me. Thank you, Dan, for that introduction. So, what I want to talk about today is the magnetorotational instability, which is an important, perhaps important, component in the accretion disks that are thought to be around black holes and forming stars. So I'm going to talk about this in terms of sort of weakly nonlinear semi-analytical framework to try to understand how the instability saturates. So this is work that I did in collaboration with Susan Clark, who's about to graduate from Columbia, and she'll be moving to the IIS in the fall. So accretion is efficient. The rate at which accretion generates energy is better at turning mass into energy than anything else in the universe, far more so than nuclear fusion. So you can get 10 to the 20 ergs per gram.
Less than annihilation.
Yes, less than annihilation. Okay, so second most. And a little bit more for a stellar mass black hole. Accretion also forms stars and planets, at least we think it does. So here on the right is an ALMA image of HL Tau, which is a protoplanetary disk. These gaps are probably carved out by forming planets. On the left is the sort of cartoon version of what processes are at work in here. There's a whole lot of them, as you can see. How these disks work in any detail is a complicated subject that I am going to ignore. Nevertheless, there are magnetic fields that thread these. These magnetic fields, they may launch winds, which may carry significant amounts of angular momentum away. I'll talk about that in a second. There are lots of different things that go on here. But for our purposes, an accretion disk is relatively simple. So I used to do star and planet formation, so I think of an accretion disk with the star in the center, but this is not the star and planet initiative, so I've fixed my graphic appropriately. Nevertheless, of course, black hole accretion disks can also be geometrically thick. I'm going to ignore that here and simply speak about thin disks. In which case, what we have is mass falling in, and angular momentum has to fall out in order for that mass to flow inwards, because of course these all of the gas parcels in the disk are on Keplerian orbits. So the part in between, how this works, is very complicated, and I'm not going to go into I'm not going to go into any detail on that, just to say one particular idea for the way accretion works, that is what drives this, is a local mechanism in which turbulence transports angular momentum. So that can be seen in analogy to convection. So here's a picture of a convection simulation for a massive star, right? You have a hot plate on the bottom and a cold plate on the top if you're an experimentalist, or you have the core of the star and the vacuum of space. The amount of heat flux that is trying to be pushed out by the core of the star is far too much for conduction or radiation to transport that heat. So instead you have actual convection here, right? So cold gas falls. I made the arrows completely backwards. Cold gas falls and hot gas rises. This is a plot of the density here in a compressible simulation. So of course the net effect of these motions is that heat is transferred upwards, and that local heat transport is mediated by turbulence. It's the turbulent fluid motions that generate the transport of heat. So the local accretion mechanism is exactly the same thing, except we turn this whole picture on its side, and instead of having thermal convection work, we have to have some source of transport, some sort of turbulent transport that moves angular momentum rather than heat. Okay, so the magnetorotational instability is one way, perhaps, to do this. This is an instability proposed originally in the late 50s and early 60s by Valikov and Chandrasekhar, and applied to accretion disks in the early 90s by Balbus and Hawley. The basic idea is relatively simple, but relies on an extremely counterintuitive bit of physics that is connected to Keplerian orbits. So if you have your accretion disk here, it is rotating differentially, such that orbits in the interior are rotating faster than those on the outside. That's the Keplerian rotation law here. The omega is the rotation rate. And it's threaded by some magnetic field. It works in more general situations than this, but this is the simplest possible one. Each magnetic field acts as a tether, and that magnetic field, of course, has tension, has magnetic tension, and that tension draws two parcels, if they're perturbed radially, one inwards and one outwards, such that angular momentum can be transferred from the inner one to the outer one. This causes the inner one to rotate faster. This is the counterintuitive bit of Keplerian orbits. If you take angular momentum away from them, they fall inwards and rotate faster rather than slower. If they rotate faster, then that continues to stretch the magnetic field and acts as a feedback, producing a linear instability. The outward blob will continue to gain angular momentum at the expense of the inner one, and the limit process of all of this is that you end up with all of the mass inside and all of the angular momentum on zero mass at infinity. Of course, that is exactly what happens. So how does the MRI work, right? That's the sort of question. We understand that's the basics of the linear instability. You can derive it very simply. But what actually happens? Like convection, of course, if we go back and think about convection here, the convective instability, the linear phase of convector instability can be written down very easily for simple boundary conditions. You can tell exactly what the critical parameter is that will drive the instability, and you will still know very little about how much heat it actually transports, right? Which is the real thing you want to know. The same question for the magnetorotational instability holds here. How much angular momentum does it actually transport? And so you can investigate this in a number of different ways. The traditional big two that most studies use are either linear analysis, where you can get the eigenmodes. These are the eigenmodes for a global, and I'll talk what that means in a second, a global geometry, so for all dynamical variables, which are the velocities and magnetic fields. You can get an eigenmode for that and a growth rate for a given set of parameters. So here on the left-hand side, these are two parameters. So kz is the wavelength in the z direction of the mode, and Rm is the control parameter that determines how strong the instability is. It's the magnetic Reynolds number, and you can get a growth rate. So here, one of these contours is the marginal curve, above which is unstable and below which is stable. So we can understand the basic idea when it's unstable, but of course a big shortcoming, there's two. First of all, we don't know what amplitude a linear instability saturates at. By definition, it grows forever. And second, we don't know which pattern is selected. So just because you have a certain kz that becomes the most unstable mode, which one of those, you could have multiple orientations, and you don't know which one it will pick. And of course, it's not just one mode that will grow in any reasonable situation. So what we want to do is understand what set of modes are actually combined to form the saturated state. The other way of doing this is numerical simulation, and I've done quite a bit of this, where you simulate the direct equations, which in this case are the Navier-Stokes equations plus Maxwell's equations in the limit, that you have, you pick a certain current and connect those two together. Those are the magnetohydrodynamic equations, and so you can get a complete solution for all of the dynamical variables, the velocities, the magnetic fields. The problem with this is we're limited by computing power to extremely unphysical parameters. So a typical control parameter, like a Reynolds number, is something like 100 to 1,000 at the absolute best. Of course, in an actual accretion disk, that number is more like 10 to the 12. And so it's a relatively large leap of faith to extrapolate between those two. Another important parameter, magnetohydrodynamic disks in particular, suffer from the fact that you have not one but two energy dissipation mechanisms. You have viscosity and you also have magnetic resistivity. Unfortunately, those two things are on themselves vastly different scales, which means that you have to simulate the whole, the largest scale, the most unstable scale of the system, and then you have to have two separate diffusion scales and resolve all of that numerically. Again, similarly, that can run from 10 to the minus 8 to 0.1 in disks. It is very, very difficult to do anything below a magnetic Prandtl number, which is the name for this combination of the ratio of diffusivities. Anything lower than really 10 to the minus 3 is an absolute floor in 3D. In 2D, maybe 10 to the minus 4. But of course, that's another 4 orders of magnitude away. So this also has quite a bit of limitation in how we understand this. So one of the things that Susan and I have been working on is using what's called the pattern forming, or what we call the pattern forming approach. So pattern formation is a common theme in physics. So we have patterns in Jupiter here. This is turned sideways to sort of get us to sort of focus on the notion of these vortices and not think about it as Jupiter with the bands. Why are there these jets and structures that are so stable despite the fact that this is an extremely turbulent system? You have the formation of sand dunes, and of course perhaps the most common or most dramatic astrophysical pattern formation that we know of is the formation of spots on the surface of the sun. These are dynamic structures that are built out of some combination of turbulence, rotation, and magnetic fields that interact in an extremely complicated way. So the pattern formation approach essentially is this. We want to describe an amplitude equation, which acts as a model equation for the leading order nonlinearities of our system. And so what we're going to do is take our state vector here, it's moved, anyway, our state vector of dynamical variables, and we're going to guess that it's of some form of an amplitude, which varies on a very slow, large spatial scale and slow time scale, multiplied by the linear eigenfunction of the system in the radial direction, and I'll talk about why that's the case in a second. And then we assume that there's a fast spatial scale that we pick a particular mode that will be the most unstable mode of the system, so that's case C. So this is our sort of our multiple scales analysis, which comes from the theory of patterns, and that basically says we're going to take two scales, a large, slowly varying scale, and a small fast scale. The fast scale is the one that carries the linear instability. The slow scale is determined by the fact that we have multiple such sets of wave numbers excited in any reasonable physical system. Okay, so we're going to try to understand what this amplitude looks like, write an equation for that, which captures the lowest order nonlinearities, the most important ones. And from that, hopefully, we can get a feel for what the most important physical ingredients are in saturating the system. And so we have a stability diagram here where we look at the wave number in the fastly varying direction for some parameter, and we have the control parameter here, which is the magnetic Reynolds number. And this heavy curve is the part at which the temporal part of the eigensolution is 0, right? So it's neither growing nor decaying. It is exactly stable, barely stable, right? And if we turn the Reynolds number up, or move into the orange region of parameter space here, we become unstable. All right, so let's flip this thing upside down, and instead we're going to pick some magnetic Reynolds number, let's say 5, that's near to the critical version. At this point now, we have some...
Is this all locally at one radius, or is this a global?
So this, I'll do both, but I'm going to start off with just a local.
This is a local.
This is a local.
Okay.
Yeah, exactly. So we're picking out some local region in R. In Z, we're allowing ourselves to vary. And what we're going to do here is we're going to use some asymptotically small parameter to take us from the stable region, where this curve now shows all of the locus of all of the modes in the system. So they're all stable, and one of them is exactly at 0 has a 0 time constant. And then we tune this asymptotically small parameter just a small bit, and what happens, we have not one mode that's unstable, but a band, it's order epsilon. Epsilon is our asymptotically small parameter. There's a whole band of these that are unstable, not just a single wave. And so the idea of multiple scales analysis is just to take all of these modes together and come up with an amplitude equation by perturbing the state vector in a certain way. Right? And so what we're going to do is we're going to calculate all of those nonlinear interactions from some small but non-discrete band. So we're not counting, these are not in a box. So we have to assume that our system is very large so that the number of waves, the number of modes in here is continuous. And then we can integrate over that continuous band of unstable modes, and we end up with some amplitude equation. So here's the basic idea, right? We have this fast varying scale, and the slow scale varies on epsilon, our small parameter, times the fast scale. So what ends up happening is this amplitude equation is something like an envelope for the nonlinear interactions of all of the constituently unstable modes in the system.
Can I ask you something?
Yes.
So your picture here is that you have multiple modes and you only have linear interactions that lead to a cascade, and that's what leads to the energy.
Yeah. I mean, so it's not going to be fully turbulent and setting up a cascade here, but yes, that's the idea.
Cascade. However, the picture that everybody's talking about following, Goodman's work back when, is that a single mode is actually a non-linear solution all the way to the end, and it's the fast parasitic instabilities that destroy the linear mode evolution as opposed to mode
correct.
Cascade. So
that's correct. But
why would it be one versus the other?
Right. Okay. So there's a couple of. I was actually going to talk about that at the end, but I guess I'll talk about it now. So here, that's true, assuming that you have periodic boundary conditions in the radial direction. Then these channel modes are exact nonlinear solutions, and thus do not have these nonlinear interactions. So there's two reasons. We were originally motivated by comparing actual experiment, where you have radial walls and channel modes do not form. And so thus, you need to do something like this to calculate these things. It need not be one or the other, but one thing that's kind of interesting, and perhaps this is a little bit of a side note, is that those channel modes, when you actually consider you don't force yourself to be in a local frame. The channel modes, so the Goodman and Shu solution, doesn't seem to actually, is easy to disrupt and hard to form if you actually have a fully global geometry. Even though locally, they certainly could. Okay, so the time scales as the small parameter squared. That's not going to play a strong role here. So let me talk a little bit about the geometry that we were interested in studying. And so here what we have is an inner cylinder and an outer cylinder. So there are a number of experiments, one in Potsdam and one in Princeton, trying to simulate to actually excite the MRI in a liquid metal. And these things are pretty simple geometry. You have an inner cylinder and an outer cylinder. You rotate them at different speeds. They're actually made out of material, so they're impermeable boundaries where fluid goes to zero, velocities go to zero. So we're simulating inside, or we're perturbing inside a domain. First, that's a narrow gap. So this is local, radially local. Here, there's no curvature terms. We assume that the gap width is basically zero. That is to say, the width L here compared to the center line radius of this is much less than 1. I'll also talk, by the way, just for those who are familiar, this is formally identical to the shearing box, which is commonly used in astrophysical simulations of this. The equations are identical. The only difference is that they have wall boundary conditions, whereas shearing boxes have shearing periodic boundaries. Okay, we'll also consider the wide gap case, where now this is actually in full cylindrical geometry. We retain all of our curvature terms, and this L need not be small anymore. And that's actually relevant. The Princeton experiment actually has relatively wide aspect ratio. It's actually a square in this domain, which is unusual for these kinds of experiments. There's a little bit of technical things. You can't have an actual Keplerian solution to this for various reasons. But you can get some part of the center. At some radius in the device, you will have the Keplerian rotation profile. Okay. So the equations look like this. These are the equations this is the Navier-Stokes equations for fluid dynamics with Maxwell's equations together. So we have an induction equation here. We solve them because we're solving for a liquid metal, which is essentially incompressible. And of course, div b equals 0 is one of Maxwell's equations. We use a stream function and vector potential to solve this, the equations look like this. There's not very much that's important here. There's a few things that are worth noting. The shear, which is actually driven, the fact that the fluid is driven by the outer walls to be at some velocity, this is sort of the ultimate source of free energy for the instability. We have nonlinear terms here. They're all in the form of Jacobian. And then we have viscous dissipation and resistive dissipation, as I mentioned. This gets rid of the energy. So we expand our solution vector. V is just a vector of all of these things in a perturbation series for our small parameter. We do a bunch of math, and we end up deriving an amplitude equation, which is remarkably similar, and it's remarkably simple. And not only is it simple, it's also a very famous equation. This is the Ginzburg-Landau equation. So using multiple scales analysis, one of the things that's very nice, of course you can actually use the symmetries of the problem and the quadratic nature of the nonlinearities and derive this right away. You don't actually need to go through all of that to do this. But the beauty of using multiple scales is that these coefficients, this is, by the way, the real Ginzburg-Landau equation, H, C, and B are all determined uniquely by the multiple scales analysis. And so long as you're actually in the regime where it's applicable, these should actually give real numbers that actually should really be the right ones. And so alpha here, of course, is the amplitude of our pattern. So that's what we're looking for. It's very worth noting, the only thing I'll note about this equation is that it itself is nonlinear. And in fact, that opens up the possibility that this equation can be linearly unstable, it can also be nonlinearly unstable, which means that once you start exciting a particular amplitude, it may itself become unstable. And so the only way that a real Ginzburg-Landau equation can become unstable is by what's called the Eckhouse instability. And in fact, when we do this, so we take this equation and we plug it into our numerical framework, which I'll talk about in just a second. When we solve that, so time is going down, this is the z direction, this is the large amplitude. In fact, we see that it goes unstable. So this is the amplitude and this is the phase of the solution, and this shows a cut at the end time here. What you can see, the only thing I'll say about this is interesting, we haven't really studied this in very much detail. The only thing that is useful to remember is that we can actually write down a simple analytical solution if we assumed that the end state was steady state in time and completely smooth in space, which obviously it's not because of the Eckhouse instability. But even if it was, it would be bounded by this, it would have this value and that value, depending on which direction the solution took. So what we can see is, in fact, that simple analytic solution gives us a very good bound to the one we actually have. So the details of this just mean that the way in which the pattern settles in is not stable in time over the short time scale. So t is the long length scale. Okay, so I just wanted to point out, this here is Keaton Burns. He's a graduate student at MIT. He's the primary author of Daedalus, which is this framework that was mentioned here. What is kind of cool about it is this is a screenshot. The thing about the way it works is these are the equations that we solve. You can see that they're just typed in plain text. So in this case, we have dx ux, and this is all these different parameters. There's no code that actually implements these as a numerical solution. You literally just type in the equations you want in plain text, it parses them, and turns this into a set of matrices which are then solved by usual sparse matrix things. I just wanted to point out very quickly, it's not a fluid dynamics code. It solves any arbitrarily smooth PDE. It uses spectral basis functions for its solutions. It's totally open source. It's developed in the open. We have a nice community. If you wanted to go use this, this is the website. That's the address. Download it and see if it works, and then ask questions. There are a lot of things we haven't done here that could be implemented in this. I've listed just a few things. I am pretty sure you can do ADS CFT. I haven't actually done any of these things. Some of them I just heard about today. But nevertheless, it's kind of interesting, and I think I'd be more than happy to talk to anybody about it. Okay, I'm running out of time. So let me just talk about the saturation mechanism. So the most important thing that we found is in going between the narrow gap geometry, which has nice symmetry and doesn't have, actually you can see the symmetry, this is the narrow gap here. This is the leading order nonlinear term. And these sort of things, the boundary layers are very strong. There's actually very little going on when you consider the boundary layers. But in the bulk of the fluid, you actually have, throughout them, you have very, very similar nonlinear solutions, which means that the curvature terms are actually not all that dominant, which is good. So let me move on from that to talk about how the saturation mechanism works. And so what we see, this is the velocity of the flow. So the dominant velocity is around the track in the disk. So that velocity gets reversed here. So if we take the saturated state and we subtract off the initial condition, we see that the inner parts get slowed down at the expense, and the outer parts get sped up. So what that means is that the way in which the MRI appears to saturate itself is by trying to reduce the gradient that drives it. This is exactly the way convection stabilizes itself. The MRI is less efficient at this than convection is. Convection, of course, pushes its solution right back to an adiabatic gradient such that it's unstable. That is not what happens in the MRI, but we do see a reduction. That is accompanied by magnetic field being pushed out of the inner region towards the boundaries. These two facts are tied together. If we had an ideal fluid, such that it had no magnetic diffusivity at all, these two things have to go together, because in that case you have the magnetic field frozen in to the fluid. Okay, and so this is the force balance that relates to that. I'll skip over that detail for now. So this is what happens because we have the perturbation theory. This is the first order, so this is just a linear solution. We can add in the second order perturbation, and in the saturated state what we end up with is a fluid structure that looks like this. These boundary layers are very strong, and there's these little jets that form at the inner and outer boundaries.
It's practically the same as the linear.
It is very close to the linear, that's right. This is very weakly unstable.
With a finite amplitude.
Correct. That's exactly right, yes. So we've also run numerical simulations. So this is actually just starting with an initial value problem and letting it run forward in time, the vector potential, the magnetic field in the plane, the stream function, which is, in fact, if your brain was good at turning these into these contours, that's what this is. And U is the velocity along the disk. And so what happens here is that this is the saturated solution, and these two things look relatively similar. That is, the numerical simulation. This is much more unstable than this because, of course, this is asymptotically unstable, which means that it takes infinite time to grow. We don't have infinite computer time at our hands, much as we would like it. And so this is slightly stronger, slightly more unstable, and it excites more modes in the vertical direction.
Why is it not fully developed turbulence?
Oh, because this is still very, very close to critical. So the magnetic Reynolds number is barely supercritical. So we're just trying to see if the weakly nonlinear approach can be validated by numerical.
So would this be kind of like Rayleigh-Benard convection?
Indeed, this is very much like Rayleigh-Benard.
Still seeing all the structure of the
That's correct.
linear mode.
That's right. That's right. And so there's actually this is in the narrow gap. The wide gap saturated state looks very, very similar as we might expect. The difference, of course, is that the wide gap is not symmetric because it's not symmetric. There's radial gradients. And the inner boundary layer here is very important as well. One of the things that this is very useful for is we are able. So one of the things. This is completely illegible. This is a plot of the magnetic Prandtl number. That is that ratio of the diffusivities, and this is approaching very small values. That's 10 to the minus 6 here, and this is the amplitude of the solution as a function of that. Why is this important? There's two reasons why this is important. One, these are totally inaccessible to simulation. It's completely impossible to simulate a 10 to the minus 6 magnetic Prandtl number. I've tried. And this point here is of particular importance because this is the value of the liquid metal that is in the Princeton experiment. So we're able to correctly, or hopefully correctly, we're able to understand the scaling out to this. So when the Princeton experiment turns on, we should be able to, when it's very weakly, in the very weak regime, we should be able to predict the proper amplitude. This is the most important plot here in some sense. This is the stress that leads to angular momentum transport, which is what the whole game is about in the first place. And the interesting thing here is that in the z direction here, up in the device, the parts which are negative and the parts which are positive are asymmetric, meaning that the total angular momentum transport is outwards, which is what we expect, or what we hope. And so this leads to a detailed prediction, which I'm not going to go into in any detail, for the amount of torque on the inner cylinders. When you actually have a lab experiment, you have to put energy in to turn the inner thing, and you can see how hard you have to turn it to maintain some flow profile. That will change dramatically when the instability sets in, and we have predictions for what that should be. So I'll just conclude by saying one of the big directions that we're moving in now is to add a considerable amount more physics in this, because it turns out that the magnetorotational instability is not only active In accretion disks, it may also be important in the interiors of stars. So with Matteo Cantiello, who's at the Simon Center in New York City, we just had a proposal accepted to look at the effects of density stratification and mean molecular weight, which are two things that, of course, are very important in the interiors of massive and evolved stars, to look at how the rotation rates, which are MRI unstable, may drive angular momentum transport in massive stars. So that's sort of one of the things that we're hoping to do very soon. And thank you very much for your attention.
Jeff, you mentioned that the simulations can approach what the Prandtl number is in liquid metal, but what are the Reynolds numbers of the liquid metal?
So the Princeton experiment will run at a fluid Reynolds number of about 1 million, which is a magnetic Reynolds number of 1. Order unity, so barely, and so the MRI is unstable at order magnetic Reynolds number order unity. In fact, getting the fluid Reynolds number to 1 million was one of the first technical challenges to meet.
So there are two possible outcomes: one that you match the experiment, and the other one that you don't.
Yes.
So if you don't, is there any physics that you didn't include?
Well, so that's an interesting question. I think. Physics, no. What I think would probably be more likely is that either the saturation mechanism is more complicated than this. I think all of the physical pieces are there, but I wouldn't be surprised if you'd have to have more orders of perturbation, for example, to get the right structure. I have reasons to think that that's not right, but of course we'll find out.
Or you can tell the experimentalists they made a mistake.
Yes, indeed. That's I'm not sure I'm that great.
So an outstanding question about white dwarfs is how they spin up and spin down. So in a lot of the circumstances, there'll be accreting matter that has a lot of angular momentum, and there's a lot of debate about how much the white dwarf will spin up and what is the role of magnetic fields. People have come down on various sides of this issue based on incomplete analyses. Do you think you could attack that problem?
Well, I think strictly speaking, no, right? Because I'm only considering the physics in the disk itself, and the interaction between the central object, be that a white dwarf or whatever, and the disk is much more complicated.
Well, this would be inside the white dwarf itself. You know, assume the angular momentum has been imparted to the white dwarf. The question is, how does that now travel within the white dwarf? How much does the interior portion spin relative to the outside? And if you stop spinning it up, how does it spin itself down?
The first part, yes. The second part, I don't think so. So the first part, as far as how the momentum gets transported through the star, yes, that would be possible. And in fact, with the sort of extensions that we're proposing to do, because of course, in a white dwarf, I don't know how the density stratification is, but I would imagine it's not 0. So in that case, then understanding how the transport of angular momentum in a system like that within the star itself is definitely possible. As far as the sort of the coupling of it to the exterior, would be beyond, because there you'd have some sort of lever arm, right? So some sort of external magnetic field, and that's not counted for.
That's very interesting.
So I think you mentioned early on that you match Keplerian only at one place.
Mm-hmm.
What exactly is the omega profile?
So it's called the Couette solution. So the constraint there is that when you spin the interior and the exterior, and you have essentially the velocity of the interior and the exterior, with the constraints of incompressibility in the fluid, you end up with a single unique solution. And that unique solution is proportional to 1/r squared, and there's also there's another term which is either 1/r. I think it's a two-term solution, and so what you end up with is that somewhere, if you match these things and you set the ratio of the rotation rates right, there will be a point at which you have -3 halves, because it changes with time. It's not just 1/r squared. There's another term.
Right. Now, in nature, in a disk, the Keplerian is driven by gravity.
Yes,
right?
exactly.
So here you're just putting 2 cylinders and spinning them.
That's right.
So, but we still think that the point at which it's Keplerian should have the same physics as the gravity-induced
So
Keplerian disk?
in the narrow gap simulations, or sorry, the narrow gap analysis we did, yes, because there it's not driven by the boundaries. In our wide gap case, it's driven by the boundary. You have the Coet solution, and there's only one point where it's Keplerian. And there, indeed, the solution is spun up by it depends on the diffusion time from the inner boundaries, and of course that's very slow. So the saturation mechanism in the wide gap case is probably not very much like it is in the disk. However, in the narrow gap analysis we did, there you're enforcing a linear shear just like you are in just the way gravity does. And so that physics I think will be similar, and should be similar. Of course, the big difference there is just because we can reach reasonable magnetic Reynolds numbers, we're still doing this at very low Reynolds number, and disks are not.
So I was going to ask you a question about supermassive black hole accretion, because there it's collisionless. And
yes.
It'd be interesting to know how applicable that is there. But the other question I had is, what is the spatial spectrum of the turbulence that you get from these kinds of experiments?
Okay, so there's no turbulence here. So what we have is, in the sense that there's not a cascade in the sense. We just have a number of unstable modes which are non-linearly interacting. So that, in the simulations, it's usually about the first 10.
But you see turbulence in a lot of accretion disks, for example.
Oh, definitely. Yeah.
So we think the MRI holds.
Yes. Oh, yeah. I mean, so if you allow yourself to go into if you drive the Reynolds number into the really turbulent regime, you definitely get a fully developed 5/3 power law type spectrum for
like Kolmogorov or something.
It's very similar to Kolmogorov. The one interesting difference though is that it is not. It's anisotropic, so it depends on the direction. Unlike a pure Kolmogorov spectrum is isotropic fully, so you can put your unit vectors however you like them. In the MRI case, in as close to fully developed as you can get. A lot of simulators will tell you that they've simulated this and they get, it's definitely turbulent and there's a cascade, but usually that cascade is less than a decade wide, which I'm because of various uninteresting numerical reasons, I'm uncomfortable calling that really a cascade, but I think it probably is. I don't know if that